With that, very happy to welcome Todd Gamblin, distinguished member of the technical staff at Lawrence Livermore National Laboratory, one of the preeminent research laboratories in the world and currently home to the most powerful on-prem supercomputer in the world. Todd, thanks for joining us on the Google Cloud Advanced Computing Community Weekly Session.
All right, thanks, Jay. Okay, I guess I'll go ahead and share. Let's see. Can you see my screen?
Yes, it's not in presentation mode, but we can see it.
Yep, okay, great. How about now?
Yes.
Okay, awesome. All right, yeah, thanks for coming to the talk. I'm going to talk about the future, the state and future of HPC software. Just first, a little bit about me. I work at Lawrence Livermore National Lab, like Jay said. I'm the leader of the Spack project, which is going to feature somewhat prominently in the presentation today. I've been involved in the exascale computing project, which is sort of where Spack grew up and became a real thing. And I'm the co-founder of the High Performance Software Foundation, which Spack is a member of, along with a number of other pieces of software for HPC. I work on the future technology directions in the Advanced Technology Office in Livermore Computing, which is things like LCAP 10. So the LCAP 10 project was in there. And also we're thinking about what should happen after LCAP for the Livermore HPC Center. And you may get a sense of that from sort of the end of the talk. So Jay asked me to talk about the future of HPC software, and I was recently moderating a panel at HPSFCon on that topic. And I think, I wanted to start with the takeaways from that panel and use that as kind of a lead off for this talk. The question that we asked the panelists, this is Michaela Telfer, Mike Carew, Martin Schultz, Christian Trott, subbing for Andy Warner, and then Brian Van Essen, was what's the biggest challenge facing HPC software right now? And I think by far the universal theme throughout all of their answers on that panel was the difficulty of integrating HPC and AI into workflows in HPC centers. It's very different from the sort of traditional HPC batch workloads, and I think that was a pretty pervasive theme. So I've tried to focus on that here. The other ones were growing hardware diversity and divergence from FP64. People were pretty worried about that, and then software maintenance in the face of the push towards AI. But I'm going to focus on the first one here. So HPC software is a pretty big topic. I am by no means going to cover all of the things to do with HPC software. If you think about the HPC software stack, there's maybe a hypervisor at the bottom if you're running HPC in the cloud. There's an operating system on top of that. There's a bunch of tools that you use to interact with HPC software, like the resource managers, things for launching batch jobs, debuggers, visualization. And then there's your typical app stack with the applications sitting on top of numerical libraries and some parallel programming models to support all that running on giant machines. This talk is going to be mostly about the userland stuff, so the apps, the libraries, and so on, and a little bit on what HPC software really needs from the cloud. So Spack is, like I said, the project that I lead. It's a package manager for HPC and AI. It is an open source software distribution built for HPC environments. And the superpower of Spack is really that it's parameterized for HPC. So instead of making or installing the build that someone else did of a package, although you can do that, you can customize it to your heart's content. You can pick your compiler, you can pick your MPI, GPU runtime, and so on for the packages. They're all set up so that the build options are exposed, and you can install something very optimized for the machine that you're on. It runs unprivileged, which is something that we care about in the on-prem world, where we're really just we're running as regular users on the machine, and it's a single tool that you can use for source builds, for installing binaries, and for development workflows. So we're trying to target a really wide range of software use cases. So it's sort of become a de facto tool that people use to orchestrate their HPC software stacks. So it's built for bleeding edge environments. It is meant to make porting faster, possibly at the expense of making installation simple. It has kind of a steep learning curve, but it's designed to get the most out of the node that you're on and to enable you to integrate software stacks that maybe haven't been built before. We get reproducibility via lock files. So if you can get something to build, then you can pin that and use it later. And that's very useful for AI workflows, as we'll see in this presentation. It has a syntax that people can use to talk about the build. That's the other sort of thing that was new with Spack, is you could talk about a lot more about the way that software was built. It introduced a syntax for talking about build options, not just versions, but build options, the target, the compiler, all the different things that go into a build in a concise way on the CLI. And it has ways to swap out multiple providers of the same interface. So if you want to build, as we do in HPC all the time for different MPI implementations, you can do that. You can swap in OpenMPI, you can swap in MPitch, you could swap in a different BLOS implementation and so on, and sort of create different variants of the same software and test the performance of them and pick the one that you like the best to run your workflow. The trade-off is really that there's a huge combinatorial space. Spack is meant to tame that, to sort of give you access to it, to let you explore it in an efficient way. It is a build from source package manager, so it is a little bit more work than what you would get with, say, pip or UV. The packages themselves are pure Python. They're parameterized, and you have one package file for each piece of software that you're going to build. So this is one for CryptKey. It's a simple full simulation package. It has several available versions. It's got 2 variants. These are different ways to build, so you can enable or disable MPI and OpenMP. And it has some dependency constraints in it as well. And then the stuff down here is really just build recipe. This is saying, if OpenMP is enabled, then translate it to this CMake option. If MPI is enabled, translate it to that CMake option. It's essentially a script to translate the configuration that Spack picks from what's up here into build instructions for whatever build system the software uses, if any. And you can script it out if your software is poorly behaved and doesn't have a proper build system. This allows us to put a lot of constraints and a lot of complexity into utility packages that you can extend. So this is showing the CUDA package in Spack. This is something that you'll never have to write and probably never want to. It gives you, and this is a very abbreviated version, essentially all the constraints for using CUDA in your package. So if you inherit from this, you get the ability to enable or disable CUDA. You get a CUDA architecture option, so you can set the compute capability that you want. And then you get all of these constraints down here defining things like which compute capabilities are supported by which CUDA versions and which compiler versions, and there's more of these in the real package, are supported by different versions of CUDA. And so that's stuff that nobody really wants to think about when they write a package that uses CUDA, and that you can just inherit in your package in Spack. And there's similar packages to this for things like Rockham in Spack. The thing that brings all of this together, we call it a concretizer. Lots of package managers have solvers. This one is essentially solving more stuff. So you've got all the constraints coming in from contributors who are building these packages, or who are contributing to the packages in our repo. We've got over 8,700 packages at this point. There's lots of rules in those. There's rules that developers, admins, users, and someone writing something on the command line can put into configuration. All of those go into the solver, and it spits out essentially a valid dependency graph that can be built. And the idea is that you specify the parts you care about, like the version, any particular options, and you get a fully specified dependency graph with all of the choices made for you for how to build it. One of the things that we have started doing is building ML stacks in CI, and we have these things called environments in Spack that let you specify pretty concisely configuration for combinatorial builds. So this is showing sort of the segments for the CPU, CUDA, and Rockham builds for x86 Linux in our ML stack. The whole stack is 155 lines for a lot of packages. So it's got Hugging Face packages, JAX packages, Torch packages, and so on, TensorBoard, TensorFlow, all in this sort of portable stack, but built for multiple architectures. And we do this for Linux on x86 64 and ARM, and for Darwin for both CUDA and Rockham. And the nice thing about Spack is it makes it very easy to write this. This is not a lot of code to maintain. You're leveraging the fact that people have written parameterized packages. And so most distros would have, say, a single config. And what Spack gives you is this parameterized package.py that you can use to sort of map onto lots of different builds in different ways. And you can see that like this is the list of the packages that you want to build. These are all just like lists of specs for these are just names of packages for different categories. And the real magic is down here where you can say like, okay, for these ones, disable CUDA and ROCm. For these ones, enable CUDA and disable ROCm. And for these ones, disable CUDA and enable ROCm. And there's a few other options that you can sort of inject into the packages, but it's all made fairly simple with this spec syntax. You can build this, reproduce it with a lock file, and what we're trying to get to is a situation where we have optimized GPU builds of all the ML libraries in Spack so that people don't even have to build this, so that we could have sort of a lowest common denominator set of binaries that are optimized for the platforms we care about, and we can make the binaries for these things default, so that you would get something kind of like what you get from pip or UV, but much more targeted to the architecture that you're running on. All right, and Spack is not just a Livermore thing or just a me thing. It's a team of probably 30 or 40 core developers across different institutions. A number of them at Livermore, over 1,600 contributors total, and this is sort of showing over time how Spack grew. And we've grown from a couple hundred packages back in 2014 to over 8,700 at this point, and it's used basically wherever there's HPC at this point. The way that I think Spack grew up, and I'm going through a little history to get to sort of the current state here, is when the ECP was kicking off, Spack kind of came around at a good time. The original inspiration for this was that I was kind of frustrated with how hard it was to build things on HPC systems. And when ECP came along, they had this deliverable that they needed to put 90 plus packages together in a software stack. And when you expand that out with dependencies, it's over like 600. And they needed to do that across 3 emerging platforms. So it's NVIDIA GPUs, AMD GPUs, and Intel GPUs across all the DOE labs. And there was not really, at the beginning of ECP, a de facto way to deliver something like this. So when we did a presentation on Spack, it was eventually selected as the thing to tie the exascale computing project stack together. And that became the glue of ECP. This is the E4S. It's the exascale, the extreme scale scientific software stack. And it's about 90 packages. Those are the red ones up here, but with 600 or so dependencies and just a mess of interrelationships between them. And this is the kind of thing that just wasn't feasible to build and maintain by hand when ECP was coming along. And there was not really a system that did these kinds of source builds for the GPUs we were targeting at the time. This also helped us tie together things like the performance portability libraries. They sort of emerged in the middle of this. They have a bunch of backends for different GPUs, but things like Cocos and Raja sort of sat in the middle and helped the ECP software run across all the platforms that we had to support. And then, since then, Spack has actually gotten a lot of adoption for HPC offerings in the cloud. So AWS, Google, and Azure all use Spack in one way or another in their HPC offerings. GCP has the cluster toolkit where you can make templates and say, here's all the Spack packages that I want to build for my cluster configuration. It'll cache it for you. And they've made that very easy by sort of integrating the Spack syntax into their Terraform configs and YAML configs for cluster toolkit. Industry contributes to it, which is nice. I think just getting the adoption that we have has helped with that. People actually want to keep their packages up to date. And cross-environment reproducibility isn't, it's not as much of a research question, I guess, as it was at the beginning of ECP. So it's been good building the community. There are a lot of things going on in the HPC ecosystem, and this is sort of getting to, that's the state. And I think looking towards the future, the workloads are changing. In DOE, in other areas, obviously, unless you're living under a rock, there's lots of AI entering into essentially all of the workloads. And DOE also has an interesting other thing going on, which is that that we're trying to connect the laboratories to function more as sort of one unified set of one unified entity to pursue these goals. And in the NNSA, there's a lot of stockpile modernization efforts ramping up alongside the traditional stewardship mission. So the simulations are being asked to do more and more things. The simulations are getting more complicated. We're being asked to work more closely with, say, design and production agencies, understand the giant data sets that they have on all of the things that they're producing, figure out ways to sort of model those, maybe ship models to the design labs like Livermore, and use those in simulations to simulate things as built as opposed to as designed. And all of that is sort of bringing more AI into our workload. And I think people may have seen that there's this Genesis mission thing spanning all of DOE. It's really just a massive push across the labs to get AI integrated into more parts of more workflows. And that involves not just traditional AI, but AI coupled with simulation. And I think before people think that we're going to go throw out all the simulations, that's not really what this is about. It is likely that the workloads at the national labs will continue to be mostly simulation, but it's going to increasingly be used to, say, train AI models, to build surrogates, to build digital twins, and to maybe integrate with simulations to replace entire physics packages and things like that, to speed up simulations, to make you could imagine taking something that might take a days or a week to simulate and turn that into something interactive with a model that you could play around with interactively on your machine. All of that is expected to speed up the workflows for designers, for people doing science, for people simulating things in DOE. And there are a lot of gaps in the HPC software ecosystem to fulfill this vision for Genesis. So one of them is that AI Stack brings a lot of new complexities for packaging. I think in some ways the AI Stack is pretty similar to how HPC simulations have looked for a long time. There's interpreted languages in HPC simulations. They're coupled with lots of compiled code, and I think that's good. Historically, in the HPC world, I think the simulations have moved a lot slower than, say, the Python ecosystem or the AI ecosystem moves. And so keeping up with the latest version of Torch, JAX, TensorFlow, all of these tools is very hard. They're fast moving. You need reproducibility for very specific versions, very specific models. Whatever experiment you did yesterday, you want to be able to reproduce again. And that can be very painful. There's a more acute need for hardware support because there are so many different kinds of hardware coming out. I mean, I think obviously there's tons of NVIDIA usage out there, but there's also things like AMD GPUs. We have a bunch of them at Livermore. There's there's TPUs, tensor processing units. Sambanova, AWS has their own custom hardware. Cerebras, all of these different accelerators. That you need backends for those underneath the AI stacks, and then you want to integrate that with the simulation, and you have a build that was already quite complicated that you now have to integrate different Python versions with, maybe newer ones than you were supporting, and then you have to make sure all your dependencies work for those Python versions. Getting a consistent stack can take a really long time, and so fighting that problem, making sure that we can keep up with what's going on in the AI ecosystem is I think one of the most difficult things about the state of HPC software. The other thing I like to talk about for the future of HPC software management is there's sort of a gap between the way that we traditionally deploy software in the HPC world and the way that, say, the Python ecosystem has come to do that. If you think about, say, pip or UV, those tools have become binary first over time. It used to be that you had to use Conda or something to get binary installs for your Python packages for the compiled ones. But now pip and UV themselves support binaries, albeit in a kind of clunky way. They bundle everything together. If you install, say, PyTorch with pip, it probably comes with a nickel or a RICL implementation bundled in there. It probably comes with 16 different GPU builds in that fat binary. And if you look at the size of the wheels for, say, for Python distributions, they can be like 900, or for Torch distributions, they can be like 900 megabytes. They struggle to stay under a gigabyte for the builds of Torch that they're distributing. And so it's kind of fast in that you don't have to build, but there's a ton of bandwidth that you have to waste downloading, a lot of code, much of which that you won't end up using. If you want to then integrate one of these binary wheels from the Python ecosystem with HPC stuff, like I said, you have to sync up the Python version, you have to sync up the dependency versions and so on. And the build that you get out of PyPI may not be a version that's actually compatible with the HPC packages you want to integrate with. So you're stuck having to build the thing from source again. And if you ever try to integrate, say, PyTorch with Petsy, it can be very picky which versions of things that you need. And if you try to put that on top of MPI, getting the ABI compatibility there to work can also be painful. There are proposals in the Python ecosystem for this. They are starting to become more architecture aware as a result of this huge AI push. If anyone's looked at WheelNext, that's something that Google's involved in. I think the core folks are from Quansight and NVIDIA, and why am I forgetting the other one? I'll remember it later. In the Astral, the UV folks, they're developing a spec that will allow tools like UV and hopefully pip and other tools in the Python ecosystem to select an optimized binary for the platform. And that'll be really good because you can get a fast installation of, say, Torch for your Python packaging tools, but you still won't get source integration. So if you want to take this, integrate it with another stack that you may be developing, that you may be working on, you would want to use something more like Spack, where you can develop something. You can say, hey, check out this package, get me the source code for it. I'm going to hack on it. I'm going to build a version with my hacked version alongside the PyTorch version and the Petsy version, the solver version, other packages that I want to build with. On the Spack side, we are trying to move towards more binary installations, especially because in Spack we have this stuff factored out. We could do much smaller packages than what they're doing on the pip side, but we're trying first to figure out what is a tractable build matrix for the HPC ecosystem right now. And obviously with all the accelerators, with all of the architectural diversity, that gets hard. So there's actually a working group in the High Performance Software Foundation right now on how we could spec something like that out. How could we come up with sort of this lowest common denominator matrix that's both portable enough that you could deploy it on many different GPU platforms, but also optimized so that you get most of the performance out of the platform without having to build everything from scratch, which can be quite painful. Similarly, we want to have more platform awareness in the packaging tools. So Spack has a feature called splicing that lets you say, hey, I'm using OpenMPI on my machine. It's this version. If you have a package that's built with a compatible version of OpenMPI, then splice that in. Use my local version of OpenMPI with the thing that was built with the compatible version so that I don't have to download, say, an OpenMPI per package like you would get with Wheels in the Python ecosystem. And so we're trying to build that out. I think this is something that'll probably happen later this year, like by the November timeframe. But this is a challenge, just coming up with a build matrix that's not too big, so big that we can't build it all the time, and that is still performant. But what we'd really like to have is sort of this seamless integration between source and binary, so that you get most of your stack from binaries. But if you want to build any part of it from source, if you want to customize anything and build that, a special version of it for your application, that you can do that. So we're trying to work towards that. This is sort of what I view as the key differences between the sort of mainstream Python ecosystem. I think they're heading to the same place modulo this sort of source issue. The other thing that I think needs to change in the future for packaging is all of these packaging systems, all of the distributions that you use on a daily basis, they require a whole bunch of toil that's sort of manual labor from people who are putting the packages together on the back end. They're all driven by humans at some level or another. Spack's parameterized, but we have people who maintain those package definitions and make sure that they're up to date, make sure that new versions get in them, make sure that the new versions work with the other things, and make sure that things pass in CI. And that getting a new build of a large stack working, like if you decide that you have a very specific thing that you want to build for, say, your HPC center or for your application, most applications are basically maintaining a software stack of all their dependencies at this point, that can be days to weeks of debugging. And packaging DSLs are useful. Things like what we write in the Spack package, they tell you the version constraints, but they, most of them model a single configuration. Like if you look at, say, RPM specs or things like that, and the maintainers inevitably miss something, right? The maintainers can't feasibly test all the configurations of the packages that they put into something like Spack or Ubuntu or any of the distributions. And if you look, at the Google Software Engineering book, they talk about this. This is a big unsolved problem. How to deal with sort of the compounded errors that you get at scale in a large software ecosystem, where maybe the developers don't understand all the configurations. They didn't put a bound somewhere. They're missing aspects. And I think humans shouldn't have to do this. LLMs are good at sort of this fuzzy contextual build information, the sort of context that it would take a human years of banging their head against builds to build up. And I think you could build an agentic system that does packaging. We've tried this a bit. We have some folks who are working on LLM packaging. There's an article in Veronix, I think yesterday, about using LLMs to package stuff in Spack. They are not quite as good at build systems as they are at, say, Python itself, or at C++, or at just regular coding. I think the LLMs really need, or hopefully they'll get over time, better training on build system information, and they need to understand kind of how build instructions in something like Spack or CMake or AutoTools relate to what's in the build tarball. They need to understand how to expand the thing, look at the build scripts, and understand how that might translate to a build system. I think that's where they sort of fall over right now. They will build sort of a template Spack package based on what they've seen on the internet. But build stuff is very, very specific, and even to like the version or the patch or whatever's going on with the particular release that you have. And so what I'd like to see is eventually, the distro maintainers have an easier life with say, an army of LLMs out there and agents going and updating the versions of the packages over time and doing what's now manual human labor. So I think this is sort of a long-term goal. So for future directions for HPC and AI packaging, I think the biggest one right now is focused on hardware and platform specialization. Packaging systems like your typical Linux distro are building for lowest common denominator, x86, 64, architectures from 10, 20 years ago. And hardware has come a long way since then, both with accelerators and even the CPUs have features that are not leveraged by most binaries. So getting more specialization there, getting package ecosystems that can support that, and making sure that installers can select a good variant from what's available is sort of the focus of projects like WheelNext and Spack. Better source and binary integration and better reproducibility. We have reproducibility in Spack, but you have to fiddle with it. A lot of configuration. You have to kind of know what goes into a reproducible build configuration. And so I think in the future, it would be really nice if you had your project and you could just say, build me a reproducer tarball for this. Build me something that I could go and just build this thing from scratch. Everything required to reproduce it is in there. I think we're close at this. We're chipping away at it, but we're not quite there yet. So that's something that we would like to get to. That and the sort of seamless, I want to hack on this piece. There's lots of tools for reproducing scientific softwares, containers, there's binary packages. They can reproduce something, but they're not always good at letting you modify it. And so like the source integration, I think, is key for that, making sure that you can seamlessly transition between something you're hacking on and something you're just deploying from, say, a release version. And then finally, the AI integration I talked about. I think LLMs can help a lot with this stuff. They need to get better at build systems. And there's actually an interesting opportunity here because in some ways, packaging systems are actually set up in a really good way for neurosymbolic AI. They're all using some sort of variant of the formal solver to resolve dependencies. And so that's a tool you could use to check, what the LLM suggests, or something you could update and see if, the thing that the LLM came up with, or say the version that you're supposed to use, if it even works, if it even resolves with the other packages. And so I think just the fact that you have these knobs available to you allows sort of an interaction between the solvers and the LLMs that maybe other systems don't have as much of a handle on. All right. So I'm going to transition a little bit from the build side and talk about distributed AI workflows and what they need from HPC centers. There are, at least in the AI world, distributed services everywhere. And if you look at how software sort of came about in the HPC center, the main thing that you use in your workload, in your batch workloads, is MPI. And so most HPC centers are locked down for MPI jobs. They have something like Munge or another sort of encryption layer sitting underneath the MPI implementation that prevents, say, other users on the same HPC system from attacking your job or stealing information. But they don't do much more than that in terms of security. And in the sort of AI world, they're coming from the cloud, where you can set up isolated networks. You can set up a set of VMs that are isolated from other VMs running on the same node. You can get your own little enclave in a cloud and not worry about who else is on it. And I think, with workloads getting finer grained, with workloads becoming heterogeneous and requiring like GPUs and CPUs, different kinds of analysis, different kinds of data, there's a much more diverse set of resources in the HPC center that you're going to want to use with your job. And so having fundamental support like the clouds do for distributed services, I think is key, and it helps support the hardware diversity we're moving towards. I think otherwise you're going to get underutilized hardware resources at the HPC center. And so, HPC centers are not really set up for these kinds of workflows, at least the way that we run them on-prem right now. If you look at your typical HPC stack, the trusted layer is generally the OS. And so you've got applications and libraries running as unprivileged users, sitting on top of an operating system. And admins manage the operating system down. You're not allowed to touch this stuff. And if you want to run something that requires, say, a privileged operation, like even installing a system package, you generally can't. You've got to do things like Spack and build it yourself in your home directory, or build it as an unprivileged user. In most clouds, you get infrastructure that isolates separate operating systems on the same node. You get virtualization. You've got a hypervisor running. You might have several guest operating systems running on the same node. And the application and libraries are above that, but the users control everything from the application and the libraries down to the OS on the node. So there's a lot more you can do. Most server-side applications are written in a way that expects you to be able to, say, listen on privileged ports or set up services that run on an operating system. And clouds are built to enable that. And so I think this is one of the things that needs to change. Virtualization overhead has gotten very low. The clouds use it in their HPC solutions, and I think we could too. And this would also allow us to better utilize the resources in the HPC center. This is one thing. The other one is just network isolation. So if you look at how clouds are set up, you can set up VPCs between VPN, or you can set up basically virtual private networks between VMs on different nodes, and those can be isolated from other things. In the HPC world, we use a simpler provisioning model, but it typically means that we divide resources up into coarse zones. So at Livermore, we have a lot of these because we have a lot of different security levels. And if you look at the node here, you can only use, say, node 1 and node 2 for stuff that goes in network zone 1. And you can only use node 3 and node 4 for stuff that goes in network zone 2. Our developers often hit issues where, like at least at our site, there's sort of a developer zone for folks who work on sort of the more sensitive applications, not classified, but still sensitive, that you don't want to put out on the more open networks. They're often forced to go over to the air-gapped network because that's where most of the compute resources are, and they can run there because we can't run their jobs on the more open network because they're too sensitive for that. And I think a lot of security concerns like that sort of constrain how you can provision jobs within the HPC center. This stuff also means that you don't get isolation between, say, two processes in your distributed AI workflow. If you set that up in one of these zones, then someone else in the same zone could, say, talk to your Jupyter notebook that's listening on a port that lets you run code. And you don't want that, because then you could exfiltrate data to another user. And I think that often prevents, some sites have scanners that say, like, hey, user, you have to shut that service down because you're not supposed to be opening ports to the HPC center. We'd like to get away from that so that users can provision something as they get it off the internet, just follow the instructions there and have it work on-prem. And so, there's a lot of cloud features. The main ones, I think, are really VMs, isolated networks, and more flexible storage, like block devices, like, say, EBS in Amazon or Google Block, where you have sort of the building blocks for all the other services. I don't think we could ever support, say, all of the services that a cloud offers, but you could provide essentially like a minimal viable stack, so that you could build on-prem the kinds of services that are being run out in the cloud all the time. And people are starting to do this. People run OpenShift and Kubernetes clusters locally. There's things like Rancher that people run at HPC centers. We're moving in this direction. I don't think we've gotten to the point where essentially there is there's not a network technology for HPC that has both the low latency and the isolation that you want. And so that's something that Ultra Ethernet is kind of promising for. We'll see where that goes. Things like Slingshot are starting to have VNIs and also provide low latency, but there's not really anything perfect for this yet. And then virtualization is something that I think is just, it's not really tested in the same way on-prem or really fleshed out the way that the clouds would run it with a control plane and everything. So I think HPC engineers need to figure out how to provide those sort of fundamental service hosting services so that we can run AI workloads more easily. So summary, future directions for HPC software, it's getting complicated. There's a whole cloud AI and traditional batch HPC simulation workload merger going on. On the packaging side, I think both sides are realizing that they need hardware awareness. They need more reproducibility, more malleability of workloads, ability to hack on things. And I think AI could actually help a lot with that. For HPC system software, I think the lift is bigger, but I think these are things that HPC centers should really start asking for so that they can better support hybrid workflows. And this isn't just for on-prem stuff. This is also the stuff that you would need to, say, interact better with services from, say, an off-prem cloud. If you want to have a server running locally that responds to, say, webhooks or something from the cloud, you need support for hosting services. And so HPC centers need that, and they need it integrated with the hardware that the GPUs are on, because more and more services require that. Stuff we didn't get to, but that you should still care about: performance portability and FP64. These are big challenges for HPC software. They're kind of beyond my expertise. But or at least the FP64 part, I think this is going to be a challenge. People are talking about things like emulation, but I could do it. I think you can invite a whole other series of speakers on that stuff. And then if you want to get involved, there's the Spack project. You can go to spack.io to get involved there. WheelNext is the Python thing. I guess I didn't put a URL there, but please visit that. It's a really cool project. And there's a binaries working group within HPSF. If curating a set of performant binaries for HPC is interesting to you, we're trying to start up a group that has some expertise on that, in conjunction with like the easy build people from the European side. So that's it. I guess I can take questions now. I hope I didn't go too far over.
No, that's great, Todd. All right, we have a couple of questions in the queue right now, and I have a couple myself, and if other folks submit them pretty quickly, we can probably get to one or two more. I'm not actually familiar with the topic of the first one, but I'm going to ask it. Madhavan asked, did the lab deploy Jules for government?
What is Jules for government? I guess I'm not sure about. I don't think I know what that is.
Yeah, I don't either. So Madhavan, maybe explain that in a subsequent question, and I'll come back to that if you submit that in Q&A again. Diarmid Buckley asks, could the Google Gemini CLI feature assist with the toil reduction in packaging? And actually, I can answer that a bit, Diarmid. We had a presentation on that last summer on Gemini CLI, and the presenter talked about that a bit. We're going to revisit Gemini CLI this summer because they've added so many extensions to that, but it is very good in builds. In terms of the toil that Todd was talking about, it probably can address some of that, but I want Todd to get into what he thinks it might be able to address since it's LLM based, and what it might not be able to address by itself, because Todd referenced the need probably for neurosymbolic AI to collaborate with LLMs on that. So Todd, are you familiar with Gemini CLI?
Yeah, and Cloud Code and Codex, all those things. I think just from having used these tools, they have. I guess it was in December. It seems like there was sort of a massive shift, and they became much more useful. I don't know when exactly in the past like 6 months or so that this happened, but I tried them again, and I've been pretty freaking impressed with how well the CLI tools can create pull requests, work on projects, understand what's in a directory on the system, and I'm pretty convinced that that's the right way to use them. I've really enjoyed using things like Gemini CLI and Cloud Code in a directory on the disk. I think that's the right place to do build stuff. I am not sure that at the moment that they fully understand how to put together a working package. I think they can iterate it on a lot, but I don't think it's really or at least I don't know of systems that have like sort of a full agentic workflow for, hey, the new version of this package came out. Try to build it with all of the relevant other packages, make sure that passes, and update any constraints that broke. And I think you also need some kind of agentic system to kind of explore around the boundaries. So like one of the things people are bad at is I build like version 5.0 of some software and I test it with 10 versions of my dependencies. I don't test like the adjacent versions to those things. I don't get the sort of end constraints on the version ranges. It would be nice to have some kind of search tool or some kind of statistical tool that sort of finds those hidden constraints, maybe based on static analysis of build systems or something like that, and updates the package descriptions. I don't think we're quite there yet, but I could see distros being maintained by agents and say approved by humans. And I think that would be really cool because it would let us move way faster, and it would give us more chances to integrate different software ecosystems.
All right. And Madhavan has given the link, and actually we probably need to cover this in the community because it's not something we on the HPC team were aware of before. Jules is at jules.google.com. It's agentic AI by Google, but this particular one, if you go to jules.google.com, it talks about when software builds itself. Jules runs continuous in the cloud, learning your code base and improving it over time. It turns understanding into action, so progress keeps happening. So in some sense, it is agentic, and it sounds a little bit like the next level of using Gemini to do this and using these open claw kinds of things. Todd, I was going to agree with you, by the way, on your response. These things really seem to get a whole lot better over the last several months, and where I've noticed they really get better is when they don't work the first time. They're incredibly good at seeing the error and fixing that. So they're trained on enough errors that they're really good at getting it right the second time. If they don't get it right the first time, they're really good at getting it right by the second. Do you have anything to say about jules.google.com? I'm guessing you haven't had a chance to look at it.
I haven't looked at it. I'm not familiar with it, but I do think that's the sort of agentic system that you would want. What it would look like in the end, I don't know. I think there's probably some specialized experimentation that needs to go on to really get these things customized for builds.
And Madhavan, I'm part of our AI for Science initiative, and we haven't talked about that particular package in that, but Google's a huge company, so I'm going to dig into that, and we'll look at potentially a presentation on that in the summer. Last question, Raghu Shankar. Todd, how do you see Helm Package Manager in Kubernetes as a transition for cloud like HPC software?
So my impression is that Helm is not doing like full dependency resolution like you would get with software. I felt like it was more of like a templating system for Kubernetes. I am not that familiar with Helm. I know what it is. But I think that's another thing that you could probably automate in similar ways. As long as you can write code for it, I think you can throw an LLM at it. I think it's good that the Kubernetes is infrastructure as code, and Helm provides you with a way to template that. So yeah, I think that's right for the same kind of innovation.
All right, let's everybody give Todd another round of applause.